Lecture 17, part 2. So in the previous part, we talked about hill climbing, which is a very simple way to find the local minimum in a large search space. And we talk about some variation that includes some kind of randomness, but those are mainly for reducing the number of neighboring states that we need to evaluate. So they are not aimed for solving the problem that we end up at a local minimum, but not the global minimum. So here, we're going to introduce another kind of randomness that tries at least to solve the problem that we reach some local minimum instead of going to the global minimum. So suppose we have something like this. Then if we start here, then if we do any version of hill climbing, then we'll end up here. We'll never be able to reach the global minimum. So what we are going to add here is we're going to add a small probability that we are actually moving up the hill. And that idea, how we define the small probability, one way of defining it is called simulated annealing. So I'll first talk about the general idea here. So every time a random neighbor is generated, so if it has a smaller cost, then we move to that neighbor for sure. It's 100% move. It's not with a small probability. So this is kind of like the first choice hill climbing algorithm that we talked about before. So it kind of saves the number of times we need to evaluate the cost of a neighbor. Also, another addition is if we have a neighbor with a higher cost, we actually move to that neighbor with a small probability as well. So in particular, what it means here is, suppose we are stuck here at the local minimum, then we can either move to the left or move to the right because they have higher costs, but there is a small probability that we actually make the move. So likely we'll move, unlikely we'll move here, but it's still possible. So if we repeat this like infinitely long, then there is some kind of very, very, very small probability that I keep moving up until we hit here, and then suddenly we can go downhill and hit the global minimum. So so that's kind of a good theoretical property. So actually, at the end of this part, I will talk about this. It's actually, we can prove with 100% probability that it will converge to the global minimum, no matter what the cost function looks like. But the problem is it's too small and it takes infinite amount of time. So in practice, we actually don't use this. Hill climbing is still better. Hill climbing with random starts, it's still better than this. So it's just has some kind of good theoretical property that we want to talk about, and that's why we're introducing an algorithm like this here. So as I mentioned already, we don't know when to stop. So we just keep doing until we find something that we think is reasonable, and then we just stop there. And if you have taken some kind of statistics courses, you may have heard the name Metropolis Hastings, and it's exactly the same algorithm. It's just a different name for machine learning people. And the name came from the annealing process of heated solids. So for example, metal. Personally, I don't really know the physics. So if I said something wrong, if you are a physics person, you can correct me, make a post on Piazza, tell me what I'm saying is wrong. So what I understand is basically if you put a piece of metal in normal temperature, then it takes a really long time to release the energy from that metal, so that at the end it takes really long time to reach some kind of minimum energy state or some kind of stable state. But if you heat this, so if you increase the temperature to make it really hot, and then you will release the energy very quick, and when it cools down, you will kind of reach the stable or the minimum energy state very quickly compared to just leave it in the normal temperature. So as I said, that explanation may be wrong, but that's basically where the name came from. So let's get back to the mathematics of actually what this is doing. So there are many choices of the probability that we are accepting a higher cost state. So remember, one very important thing is if we reach a lower cost state, we always go. But if we reach a higher cost state, then we use the probability. So one way is to use the constant probability, and it turns out the performance is not great. So we should probably change the probability over time. And 1 over t sometimes is too fast. You need some kind of constant in front to control the speed. So one way that turns out to be a good way is use a formula like this. So it's related to the distance between the cost, so the difference between the costs from one state to another. So for example, the probability of jumping up by a lot is kind of small, and the probability of jumping up by a little could be larger. So that's this term here. And we add some kind of increasing function to time. So it's similar to this 1 over t idea, but we just want to add some kind of non-linearity, or at least some kind of constant coefficient in front so that we can control it. And then we put an increasing function, exponential function outside as well. So it's basically the same idea as decreasing over time, but it's just a particular function that we chose that we think is kind of reasonable to put. And that particular choice of probability of moving to a higher cost state is called simulated annealing. And there are many things we can choose. One example is choosing a temperature. So the temperature can increase or decrease arithmetically, which means each time I decrease by a fixed number, it can be 1, it can be something else that we choose, or it can decrease geometrically, which means it's we add a multiplicative constant in front, and every time it decreases by that amount. So the problem with this is at the end, when temperature becomes 0, when this temperature becomes say 1, then we can no longer further decrease it. So that may be good, that may not be good. And here we can just keep decreasing it, and it's getting smaller and smaller, but it never reaches 0. So let's actually look at the function again. Let's get back. It's exponential of the difference minus the difference between the costs divided by the temperature. So let's see. If we have a high temperature, it means this T is large, so that the whole fraction is small, and then minus that fraction is large, and then the whole probability will be large. So when the probability is large, it means no matter what state, whether it's higher cost or lower cost, we will always accept the change. So basically, at the beginning of this algorithm, where the temperature is high at the very beginning, we're just basically moving randomly in the state space. And that's what I mean by always randomly accepting any neighbor. So we're basically moving among the neighbors randomly. And later, when the temperature gets lower and lower, then when temperature is decreasing, this whole fraction would be increasing, and you have a minus sign in front, so the whole thing is decreasing. So the probability of moving to a state with a higher cost is decreasing. So at the end, it's kind of close to 0. When it is exactly 0, it means we're just trying random states and find the first one that decreases the cost. That's exactly the definition of first choice hill climbing. So when the temperature is lower at the end, near the end, we're just doing first choice hill climbing. And that's a page that summarizes this, and it's just combining the formulas. And let's talk about the performance. So the same as hill climbing, the design of the neighborhood is actually the most important one. So how do you define? Would you define a large neighbor a large number of neighbors, which is basically like I'm still searching through a lot each time, or we have a small neighbor, which makes more steps, but maybe it converges to the minimum faster. So that design is very important, and unfortunately, it's different for each different application. So I don't have anything to say here. It's just for each problem, you need to design the states and the successors so that the search process is the most efficient. And as I talked about this earlier, if you have an infinitely slow cooling rate, so basically I think it means the probability would decrease very slowly, which means there is always like a positive probability of moving to a higher state. Then with probability 1, we will be able to find the global minimum. Again, this is theoretical. What I mean by probability 1 is it may take almost infinite number of steps, which is not feasible. So that'll be why, in general, in practice, we never use this. We just use hill climbing.